So I'm Darshan Patel from Fujitsu. So specialize in confidential computing and AI ML infrastructure. So I am here with my colleague Tatsuya Kitamura, who is joining me online today, who is also specialized in confidential computing, working from Fujitsu Japan. And we are here at OC3 for the first time, and we are really excited to discussing about the advanced secure processing with Fujitsu Monaka and ARM confidential computing architecture. So as the sessions move ahead, we will dive into more into like how the CCA is evolving, its innovation, and our open source collaboration with Fujitsu Monaka. Let's move to the agenda. So today I'll be talking about I'll be introducing Fujitsu Monaka and how the ARM CCA for Fujitsu Monaka is helping for the confidential computing and data in secure. And I will be demonstrating a thread model demo. So we have been seeing like a hypervisor is out of the trust boundary and giving a thread to the model. So how this exactly work, and so I'll be demonstrating that. So we have a video over there, and what like I'll be discussing on the basic ARM CCA software component. It's mostly like what are the software components that need to be enabled for the CCA. We'll be discussing more on that, and the practical tool for the ARM CCA, which is like KMU. I'll demonstrate that also, like how you can create a ARM CCA virtualized machine, as there are no currently hardware supported ARM CCA. So you can use that for like virtualization and create a CCA ARM related realm machines. And then our Fujitsu's contribution to the ARM CCA, like to the open source community, what we have done. And then at last, if time permits, we'll have a Q&A. So like computing technology that underpinning AI innovation, like Fujitsu is performed from like since very beginning on the, like we started from the enterprise system in 1990s, and then moving forward we had a K computer and Fugaku, like basically a supercomputer. And now we are here with the next generation processor, which is the Fujitsu Monaka. And apart from the classical computing, we are also investing into the quantum computing. Like we have evolved through a many core to memory-centric computers. So today I will be presenting Fujitsu Monaka. So our next generation Fujitsu Monaka is ARM v9a architectures. Basically, ARM it supports ARM SV2 for AI and HPC. And it has the 3D chiplet technology, which has a core die of 2 nanometer and SRAM die and IO die for 5 nanometer with ultra low voltage efficiency technology. It comes with a DDR5 12 channels, which like 144 cores per socket and 288 cores per node. It also supports like PCI Express 6.0 with CXL 3.0. Like it is like high-speed performance processing platform. It's 2x faster than competing CPUs when it will be like to be shipped in 2027. So like balance of the energy efficiency and performance, we are like on the significant CO2 emission, radiation, and power cost with high energy efficiency. And like we are our aim to have like utilizing ARM software ecosystem to have a ease of use. We are having our like self-designed microarchitecture and ultra low voltage technology. So basically, our Fujitsu Monaka software R&D, like we are initiating a co-creation with diverse domain to contribute toward a sustainable digital transformation globally. And with ARM-based CPU Monaka and open source AI software stack, we are planning like trying to innovate for meeting a growing AI demand of data center and pursuing 2x performance for energy efficiency compared to the competing CPUs. So now I'll be introducing the ARM CCA for Fujitsu Monaka. So like the key technology is here is per VM encryption. Like there will be no access to the from the cloud operator because the processor encrypt each VM memory with a different key will not allow any user to access data from the cloud operators. And because the processor will be here root of trust. To achieve this, Fujitsu also joined CCC, Confidential Computing Consortium, since 2024, and we are collaborating with ARM, Linaro, and OSS community for software stack enhancement. And Fujitsu's focus on development area like confidential AI and confidential VM and containerizations and remote attestation to provide a verifiable trust. So next, I will be showcasing a thread demo. Basically, this architecture you have seen in the previous ARM CCA demo also. Like there will be a two-state, non-secure state and RAM state. So there is a new introduction of granular protection check, new data structure, which is called granular protection table, has been introduced into this architecture, ARM v9a. So here the RAM state can, if you see the green arrow, it can access the GPC and its physical address space. And non-secure state of the application can access its non-physical address space, but hypervisor can't access the realm physical address space, but it can still access the realm physical address space. So for creating this demo, we have created a malicious script running inside a hypervisor so that it can, like, we can showcase like how it can see the runtime data from the physical address space of the non-secure state, but it can't see the physical address space data for the RAM state. So I'll be like doing a demo here. So first, we required a two terminal to showcase like the guest OS and the host OS. So in the guest OS, if you see, we are running a client secret application, which will take input from the client in the guest OS. Like we are writing our secret into the physical address space, and then it will, and in another terminal, we are in the hypervisor, we have a scan RAM malicious script, which will try to scan the data in the physical address space of the non-secure environment. And it can, like, basically it can found the pattern, and it will print the ASCII character of that secret text that we have written from the guest OS. So in this scenario, we have seen like how, in non-secure state, it can find the data. Sorry. Can you play the video? It's not playing. Yeah. So basically, in non-secure VM, the client secret app, it will write the secret text, which will load into the memory of the non-secure environment. And the scan RAM, which is a malicious script running inside a hypervisor, will try to scan the pattern and try to print the data that has been stored into the physical address space of this. So next, after running into non-secure state, the same experiment we will try to do into realm state and see like how that happens, and like client secret, can this malicious script able to read or not. So once the client secret app is running inside a secure RAM, and the secure VM will have a GPC specifically here. So once the secret data is loaded into the memory, and malicious script running inside the hypervisor will try to do a scan of that particular RAM, it will run into a sec fault, basically. So sec fault is because of the driver. But exactly if we see the log, the D message, if we check for the particularly the kernel log for this, then we can able to see that the issue was due to the granular protection fault. So this granular protection fault was introduced into ARM v9a architecture, which will a specialized structure which will protect the physical address space from the hypervisor. It will not get access from the hypervisor also. So this is the one of the protection that been added into the ARM v9a architecture. On top of this, there is a memory encryption context also, which will do like per VM memory encryption based on the key which is derived. So next, I will showcase like the basic software stack that will be required to enable the ARM CCA software component. So on the base of the rack, there is a hardware Fujitsu Monaka, which is Fujitsu is developing and is going to be shipped in 2027. And on top of that, there is a TFA and TFRMM. So TFRMM is specifically a new kernel which firmware which has been introduced for this specific ARM v9a architecture. And on the Linux kernel host, like we try to enable two flavors basically, confidential VM and confidential containers. So the KMU EDK2 and Linux guest kernel is developed and contributed by the other OSS community, and we are mainly focused on the libvirt, kubevirt, and OpenStack of the confidential VM. And similarly, for the confidential container, we are trying to enabling the guest component of the confidential container. Together with this, we are also providing like a remote attestation service using a Verizon and Trusty. So Trusty specifically for containerization, and Verizon, like we are using currently a Linaro hosted Verizon service. So this is the practical tool like KMU, which has been enabled by the Linaro. Here we are using a verification service as a Verizon, and a CCA workload attestation tool, which is a POC, has been created to demonstrate the CCA attestation workload. So in this KMU simulation, we have simulate the KMU based on top of the x86 hardware, and using that we can spin off the RAM VM, and we can run any application inside the RAM VM, and also by CCA workload attestation we can do a attestation service. So I will try to demonstrate this also, like how you can use a KMU to enable your ARM CCA and run any application on that. So we have followed the building RME stack instruction that has been provided by the Linaro. Once you will log in into the host OS, it will spin off a 4 terminal, basically a firmware, realm, secure, and the guest OS. So on the firmware, the terminal will be it will showcase all the firmware logs, and in the host you can log in with the root user. It doesn't require a password. So once the realm command you will start to spin off, the realm will be started, and you can able to log in into the realm machine. So this will be spin off by the KMU VMM, and once the KMU VMM will help to spin off the realm machine, we can do a login into that and do a attestation. So in attestation, we will try to demonstrate both the model here, the background check model and the passport model both, that you can able to do. After once the realm is up, and so these are all the logs which are flushing while you will up the realm machine. So once the you are logging into the realm machine, you will able to do a attestation basically with CCA workload attestation. It will help you to get the evidence from the realm VM, and then you can pass it to the any relying party for the further verification. So this can be sent to the Verizon or any other like trusty third-party verifier service. And then after the report is generated, it will give a EAR status. If it is affirming, then the verification has been passed. If it is fail, it will show as a problem or a contradicted statement. So here we can see that the status is affirming. So this was like evidence generation on the realm machine using the tool, and this can be passed to the any relying party for the further verification. Next, we have done the passport model. In the passport model, like it will be verifying, the tool will be verifying, and the verification report we can send to the relying party. So that will be our passport model. So next, I will try to showcase to run an application inside a realm machine. So here we have simple k-mean model we have tried to run to showcase how any model inference you can do in the KMU simulation also. So here we will try to running a k-mean clustering model inference. So in this way, you can do on non-CCA hardware, you can create a realm machine and you can run do attestation and run application. So in this demo, like until now, there is no ARM CCA enable hardware is available. So all the development activities we are doing on the KMO environment. So, so now coming to the Fujitsu's contribution to the ARM CCA. So the component which are marked in the green, you can see. So for the Linux kernel, guest OS and the host, we are doing a collaborative assessment with ARM, like latest V7 guest patches based on RMM 1.0 for host and guest OS. Both are available in February 2025. And for the KMU, we are doing a collaborative assessment on enabling with the Linaro. So the patches are almost finished, and we are going to release that. And for the libvirt and OpenStack, we haven't seen much development activity related to CCA. So Fujitsu take initiative and release the latest V2 patches on the libvirt, which support the CCA. And the patches are available in Feb 2025. And for OpenStack, we have submitted a design to the community, and we are working on the feedback. Specifically for the libvirt, as it was necessary because it will enable CCA support for the KubeVirt, OpenStack, and other component where libvirt is going to launch VM. So we have added a new tag, launch security type CCA, in the libvirt, so it can detect and in the YAML XML schema we have added it, so it can detect the CCA related hardware, and it can spin up the VM. And we have used this based on the KMU QMP to query and configure the CCA VMs. And also we have written the test cases to verify this if CCA related support is not getting broken. So the test cases is also is merged and available into the latest patches. So I'm on the concluding slide. So we are like continue contributing to the enabling the ARM CCA support, mostly focusing on the libvirt, OpenStack, and KubeVirt and other software component. And Fujitsu Monaka, like we are aligning with our commitment for the grid center data goals and democratizing confidential AI for sustainable digital transformation. And we are doing like and welcoming the feedback and contribution from the confidential computing community. So Fujitsu look forward to actively collaborate with to accelerate the ARM confidential computing ecosystem. So these are the so this achievement, like this is the acknowledgement. So this achievement was obtained as a result of the grant project by NIDO, which is a new energy and industrial technology organization from Japan. And these are the resources, so you can scan the QR code to know more about the Fujitsu Monaka and the libvirt development that has been submitted to the OSS, and also the building stack for the ARM CCA software stack. So yeah, on this I'm completing my talk. Thank you. Thank you, everyone.